Welcome back. So in previous lecture we discussed mostly about the different type of magnitudes, and at the end we discussed about the importance of the moment magnitude and how the moment magnitude has been calculated using seismic moment. And this is one of the most accepted magnitudes scale, that is your moment magnitude. And further, if you look at the magnitude, then in terms of the energy, so usually we take the magnitude as a measure of the size of an earthquake, and if you increases the magnitude by 1, then the energy is about 31 to 32 times larger. So if it increases by 2, then the energy is about 900 to 961 times, and so on. So you can make out with this that how much amount of energy will be required or required to suffice 1 magnitude earthquake, or maybe you can say 2 magnitude earthquake, and similarly with the 1 magnitude. So this is the just to make you understand the table, that you have the multiplication factor you have of 30 to 31 or 32. And in case of the Hiroshima atomic bomb which was been released, the amount of energy which was been released was equivalent to 5.5 magnitude. So this is almost a very small magnitude earthquake. So you can understand that how much amount of energy will get released when you are having the earthquake of 8 magnitude. So seismic energy, both the magnitude and the seismic moment, are related to the amount of energy that is radiated from an earthquake. So Richter, working with Gutenberg, developed a relationship between the magnitude and the energy. So this is helpful when you want to understand that how much amount of energy is really required to suffice. And for example, if you are having, so this is the equation which has been given, log E is equal to 11.8 plus 1.5, this is a magnitude m. So if suppose you are having the earthquake of 8 magnitude expected in the region, and you are having several numbers of 6.5 magnitude earthquake which are occurring, then you can, based on this, you can calculate that how many earthquakes you will require to suffice the energy of earthquake with magnitude 8, and how many earthquakes in the 10 sense for 8, how many earthquakes of 6.5 will be required. So even 6.5 earthquake is considered to be a damaging earthquake in some of the regions where we are having poor construction and all that. So but the ongoing deformation is capable of causing an earthquake of magnitude 8, then several numbers of 6.5 magnitude earthquake occurring in that region will also not be able to suffice the amount of energy which is required to trigger an earthquake magnitude of with 8. So this is the scale and the relationship which has been given here. So this side it shows the amount of energy equivalent to in kilograms of an explosive, and this is the scale which has been given here, the magnitude scale, and you are having the earthquakes which are between 8 and 9 or greater than 8 are considered to be great earthquake, and then above 7 up to 8 has been considered as a major earthquake, strong earthquake, moderate, light, and minor one. And in top here, so if you look at in some of the literature, mostly you will find that the Sumatra Andaman earthquake of 2004 was 9.3 and very close to the so far considered as a second largest earthquake, that is in 1964 Alaskan earthquake. and the largest one so far recorded, 9.5, is the Chilean earthquake. Now further, what we have seen in the previous slide, that we talked about the energy release during 1 magnitude earthquake and the next higher one. These two graphs, it shows that the relation, what is the relation between the magnitude and the displacement on the fault, and the magnitude and the surface rupture length along the fault. So this is on the fault and along the fault on the strike. So if I have to put the sketch here, then what we are talking, that this is the fault trace on the surface, and the amount of displacement which will be seen on fault is your rupture length. So I'm just putting in a block diagram here. So this is the amount of slip you are going to expect during a particular earthquake, and then rupture on the surface. So this is what is in the length in kilometers. Okay. So in both the cases, what we see is that if you are having the larger magnitude earthquake, then larger will be the slip on different type of faults, which you can make out based on the curves which are been given here. So in case of the reverse fault, in compressional tectonic environment, in extensional tectonic environment, along on the normal fault and along the strike slip fault, when you are having the shear or any two plates which are passing, or the block of the rocks passing with respect to one another, so along the horizontal plane. So you are having different curves which have been given here for red. So you are having like if you expect an earthquake of 7.5, then the displacement which is expected on the fault will be around 10 meter. And then similarly with the 6.9 or so, then you are having the different. On the strike slip fault you will have less than 1 meter, on the normal fault you will have almost 1 meter, and in case of the reverse fault, that is also almost like 1 meter on fault. So and further on the other graph, if you see there is comparison given between the magnitude and the surface rupture length. So in case of your Chilean earthquake of 1960, the magnitude was 9.5, and the rupture which was experienced was around, for almost length was 1,000 kilometers. Now if you extrapolate this line and say that okay, you will have a magnitude of 10, which is till date not recorded at all, but if this occurs, 10 magnitude, then the whole circumference of the earth will be covered. So the rupture length will be of almost like 40,000 kilometers. So by the number, the energy of different earthquakes, to compare energy between different earthquakes, a Richter magnitude difference of 2, 4, 6, 1, and then so on, if you go, then you will be able to understand that how much energy it will be required if you are having, like for example, if you have 2 magnitude earthquake, then the energy is around 1,000 times the energy of this one, and then you are having 4 magnitude, then it increases by this amount. Okay. So energy released during an earthquake, each whole number increases in magnitude corresponds to an increase in energy released by approximately 32 times. So example, 32 magnitude 6 earthquakes. Okay. So 32 number of magnitude 6 earthquake would be necessary to equal the total energy release for 1 magnitude 7. So that is one number of magnitude 7 earthquake. So you can imagine that just at you are increasing the magnitude by 1. Okay, here you are having 6 and you are having 7. So if you are having 1 7 magnitude earthquake, you require 32 number of 6 magnitude earthquakes, because again the moderate magnitude and this large magnitude here. Similarly, more than 1000 earthquakes of magnitude 6. So you will require 1000 number of magnitudes. Earthquakes of magnitude 6 would release energy equal to a single earthquake of magnitude 8. So you can imagine that the Himalayan region is capable of triggering the energy which is available based on the deformation pattern. The Himalayan region can trigger earthquake of magnitude 8, and if you are having continuously about 1000 earthquakes, that will be able to suffice the energy of only single 8 magnitude earthquake. So this is the difference between the magnitudes and the amount of energy. So sometime we feel that we had enough number of 6 magnitude earthquakes, so energy is completely released in that region, and you cannot expect having 1000 earthquakes in that particular region. So the energy will always remain available, or the strain accumulated will always remain available, even though we are having large moderate magnitude earthquakes, large number of moderate magnitude earthquakes which are occurring in that particular area. Now, ground's acceleration and shaking time. The acceleration is normally designated as some proportion of the acceleration of gravity g. So 1g is the acceleration felt by a freely falling body. Now this is important because when we are talking about the ground shaking, and ground shaking or seismic shaking will result into the movement of the Earth's surface, and that will result into your total damage or partial damage. So most earthquake acceleration are less than 1g, a few are more. An increase in magnitude above 6 does not cause much stronger shaking, rather than it increases the area and total time of shaking. Like for example, earthquakes of magnitude 5 generally last for only 2 to 5 seconds. Those of magnitude 7 from 20 to 30 seconds, and those of magnitude 8 almost like 50 seconds. So if you are having like the weaker structures, this time duration of ground shaking during 5 magnitude earthquake will not result into the damage. But if you are having even 7 magnitude earthquake, then the time duration for the shaking is around almost more than around 10 times more. So you are having 20 to 30 seconds, and in case of the 8 you are having much more, up to 50 seconds. So mostly the ground acceleration will result into toppling of the structures or damaging the structure in total. So this is an example of 1906 San Francisco earthquake. Magnitude was 7.8. So a magnitude 6 earthquake shaking usually lasts for only 10 to 15 seconds. It provides only a short time to evacuate, because you need to plan for the mass evacuation. So this will provide a very short period, okay. Whereas the magnitude 7 earthquake provides more time, but evacuation is harder because the ground shaking will be much higher and acceleration will be approaching about 1g. So the longer shaking lasts, the more damage occurs. Structures weaken or cracked in the first few seconds of the earthquake are commonly destroyed with continuous shaking. So this is what I was trying to explain in case of magnitude 5, that the time is less, so the weaker structure will withstand. But if you are having the longer shaking during large magnitude earthquakes, so more damage usually occurs, because the initial stages the structures will be weakened or cracked, and if it lasts for longer period, then they will be destroyed. Commonly such buildings will be destroyed because there is almost no time to evacuate, and because running outside can result in death by falling debris, it is generally best to duck under the study desk and all that. So this portion comes under the safety measures. So you can put yourself under the desk or any hard or sturdy objects which can make you or which will allow you to be on the safer side from the falling objects due to ground shaking. So one of the effect of earthquake, that is 1964 Niigata earthquake of magnitude 7.6, and 1999 Izmit earthquake. This was from Turkey. So secondary phenomena which has been seen here is the liquefaction, and the another one is the damage pattern. This is mainly because when the damage, both the damages were related to the secondary effect, and that is the liquefaction phenomena. 1964 Niigata earthquake and 1999. This is from Turkey, and this image is from Japan. So if you look at the comparison between the modified Mercalli scale, the intensity has been given here, and the details which we have already discussed for different intensity, and the expected ground acceleration which has been listed here. So this, like for example, you are having 7, intensity of 7, the damage is negligible, and the ground acceleration will be ranging between 0.1 to 0.15 g. Whereas in case of you say and similarly this will keep increasing, and if when you are having the intensity of 10 or 12, then the ground acceleration will be more than 1 g, and this is extremely dangerous. So I'll end here with this topic, and we'll continue with the new topic on active faults and active fault topography in the next lecture. Thank you so much.